Hi everyone, I would like to present our paper on our hierarchical approach to pest detection using few-shot learners and small data set. So this presentation is going to be done, the first half is going to be done by myself, and the second half will be done by Stephan. So the computer science department at Pretoria's University of Pretoria partnered with University of Pretoria's Forestry and Agriculture Biotechnological Institute, FABI. And the goal here is they're looking to build an insect detecting model or software that can help farmers in identifying pests in the wild and to help them with how to take the immediate action once the correct pest is identified. In this particular problem, the pest we focus on is going to be the Sirex and Gonipterus. So these pests are local to the South African context. And the project focus would be on constructing our hierarchical classifier for both of these insects. In the best case scenario, the goal of the model should be to identify the insects correctly, especially across the various stages of their life cycle. But in the worst case scenario, we're hoping that the model is able to detect some common features of these insects whenever it fails to detect the actual insect. So this project follows a normal data science project lifecycle. So the first step is obviously acquiring the data. Once we have the data, we do an exploratory data analysis on it. Next, we model it. Then we deploy and we create some visuals around it. And from this deployment and visualization, we then derive the results. And this is the iterative cycles. So the data set that was provided to us by FABI contained both the Sirex and Gonipterus pests. There's about 142 Gonipterus and 42 Sirex pests, and it's across the various life cycles of these insects. In order to further enrich this dataset, we are using the IP808 public insect dataset, which contains about 75,000 images of insects belonging to 102 classes, where 19,000 of these are annotated with bounding boxes. So before starting the modeling, it's worthwhile always to explore the data to make sure that the data we received is indeed what was promised to us. And the other reason why we want to explore the data front is to see what possible features a model might detect. So for this particular project, we looked at analyzing the RGB channels of each of the images, as well as doing an edge detection across the images to see if there might be any distinct features being detected in that sense. We also built a very small predictive model, which is not an object detector, but just a classification model, which can classify whether the image contains a certain insect or not. So in order to train a full model, we created a backbone model. The backbone model was created by using the YOLO V8 model architecture and training it on the IP808 dataset. Once this model was trained, we then used it to train specific feature models as well as the lifecycle model, which is our primary model, using the data provided by FABI. So we looked at both, for example, just object detection in terms of the Sirex and Gonipterus pest, their various lifecycle, but also trained it specifically. If it fails to identify those two insects, we wanted to identify certain features. And the idea behind these features are that these features then give a short list. So even if the model doesn't detect the actual pest, it still gives the researchers a short list so they can more quickly and accurately see what was detected on the photo and use the combination of features to derive the possible pest that might have been detected.
So the next step is deployment and visualization. In order to give the project partners a view of the model, we built a basic web application using the Python Streamlit package. This application allows users to select a confidence threshold for the model and then to upload an image or select an image from a list of sample images. Model predictions are then generated for the chosen image, and the summary of the predictions is printed. Additionally, the predicted bounding boxes are drawn over the original image and is shown next to the original image. Visualization is discussed in more details in the results section. So the Streamlit app allowed the project partners to interact with the model, test out different thresholds, and see how the model performed for different types of images. Moving on to results, we see that the primary model performed well for the Gonipterus, but performed poorly for the Sirex. So the model achieves an F1 score of 0.86 across all life cycle stages of the Gonipterus, up to an 80% confidence interval. For the Sirex, however, the model fails to achieve an F1 score over 0.75, getting progressively worse at higher confidence levels. The hierarchical output structure hopes to address this issue, as the feature models can potentially generate useful predictions, even if the primary model fails to identify the insect in the image. So on the right, we see the F1 confidence curve plotted, with the dark blue line being the overall model performance. And we can see that all three of the Gonipterus life stages are perform better than the average, whereas the Sirex at the bottom two lines perform much more poorly and drop off rapidly after 0.6 confidence. For the secondary models, the feature models, we see these performed well, generating high confidence output even when the primary model fails to make a prediction. Specifically, the insect and larva models both achieved F1 scores of 0.93. The Sirex adult and Sirex larva models also achieved high F1 scores of 0.98 and 0.95 respectively. These models, however, struggled a bit in terms of false positives on images of other insects. Flying insects presented the most difficulty, with the flying model achieving an F1 score of only 0.69. This is likely due to bounding boxes for insects with open wings, including a large amount of background, thereby allowing the model to overfit on features that's not necessarily part of the insect itself. The wings model was therefore built. This was an experiment to evaluate whether segmentation could address this issue, but the model failed to achieve reasonable accuracy due to us only having 14 images suitable for training. In conclusion, the primary model performs well for the Gonipterus, but performs poorly for the Sirex. The feature models are able to generate valuable predictions even when the primary model is unable to generate a prediction of high confidence. Winged insects present the greatest challenge, as the dataset contains a few images of winged insects and the model is prone to overfitting on the background around the wings. To improve the model, the project partners can work to expand the size and improve the balance of the dataset. Furthermore, the impact of segmentation can be explored further. Finally, the model can then be deployed as a mobile or web application, thereby exposing it to more users and better helping to detect pests in the South African forestry industry. That brings us to the end of our presentation. Thank you so much for your time.